Alright, guys. So next week I have to travel to New York City for the IBM conference, from Wednesday to Friday. So Tuesday afternoon to Friday. So where I will still be able to do the lab. But after the lab, I have to rush to the airport. So I will have a Monday lecture. Let me see. Did I update this? Oh, I did. So Monday there will be a lecture, and for Tuesday the lab I'll be there to help you guys out, and for Wednesday and Friday I'm gonna record a lecture and post it. So it's different from microcontroller. The microcontrollers, I just have the tutorials posted and the students will just go to 610 to work on their assignments, right? But for this one, it's a lecture-based class. We do need to post lectures. I'm gonna post lectures to Wednesday, Friday for you guys to watch. And also, I believe that it's gonna be too painful to watch the lecture for 55 minutes. So it will be a little bit shorter, and I'll just pick up the important things to cover, make it short and very concise. So you guys watch the lecture and do some homework assignments. That's it. Okay. So we're not wasting your time next week. So so in that case, no quizzes next week. Give you guys a little break, but there will be a quiz today and a quiz Friday this week, and the homework 3 is due 24th, which is Wednesday next week. So you guys do have a lot of things to work on. Okay, I believe I'm still keeping you guys busy. If I'm not, just let me know. Okay.
Not too busy.
Huh?
Thank you.
Thank you. Okay. Yeah, hopefully, yeah. I think the pace is still okay. Is that the case, or is too much by far?
It's okay.
It's been okay. Yeah, it will become a little bit heavier towards the end of the semester. There will be a lot of cadence tutorials. Okay, cadence tutorials to follow.
You know when we're gonna sign the NDAs?
NDAs, yes, I will start working on that. I don't know, tomorrow. Always tomorrow. So much to work on. What's that? No questions?
Oh no,
No?
I'm just scratching.
Huh?
Tomorrow's gonna be busy.
Tomorrow's busy. Yeah, every day is busy. Every day is busy. So busy. All these trips. I used to hate trips, but now I think it's important, and it's important to meet with those people so we can bring all this knowledge back, right? So for these, I think the IBM conference in New York City is in Manhattan. That's one of the flagship. I think they built that flagship headquarters for IBM in Manhattan just a few years ago. That was one of the biggest branch for IBM. And I was looking at hotels in Manhattan, and it was $700. I was thinking about that was 3 nights, but eventually that was 1 night. Yes, I mean $700 is a cheaper one. I saw like $2,000 and $2,500 just for 1 night. That's crazy.
If you find a hotel for like $200, you'd be next to some crackheads.
I think so. Yeah. So so definitely I won't stay there. So by the airport, which is 18 miles from Manhattan, can get Holiday Inn, all these hotels with like $150, and just regular ones. So that was a shock.
Will we have a midterm in this class as well?
Yeah, we got midterm, we got a final. Midterm is going to be here. Yeah, final is here. 2 exams, a lot of quizzes. Yeah. So today we're covering the stick diagrams. Okay, very important topics. Stick diagrams. And there will be a quiz on passing gates, transistors, switching point, all these kind of things. Any questions on this?
Do we need to have all of these formulas memorized?
For what? For quizzes? For the square law equations? No.
Okay.
Nope. But you need to know that BGS has to be larger than threshold voltage, right? Has to be larger than VTH in order to turn it on.
Mm-hmm.
And whenever it's lower than that, they shut it off, right? That's it, I think.
Okay.
Yeah, that's it. I got started?
Yeah. Let's do it.
I'll give you some examples on Monday regarding the AOI logic, building schematics using NMOS and PMOS transistors. So just giving you a little bit more examples, like XOR gate, for example. XOR gate. Remember how we build XOR gate. So as the XOR logic first, you got the result Y output equals A not B or A B not. Let's compare it. If we use a regular way to build it, compare with the AOI logic and what the differences are. So this guy, we got A, B, two signal lines, and we invert one, so get A naught. Same here, B naught. So A naught and B is an AND logic. A B naught is another AND logic. And finally, these two results getting ORed are getting Y equals A naught B or A B naught. Okay? So we'll start building the layout. Do we know NAND gates? Do we know inverters? Do we know AND gates? We know all of them. We learned that on Monday and Friday last week, right? So we know these schematics for all the gates. So now start building it. Keep in mind, when you build circuit, when you build layouts, you put them in the same. Do I have the picture of that? Let me draw it for you very quick. Okay. Just one quick example, just show you guys how this is being organized. All right, so here's a chip. Here's a chip. Okay, the silicon die, and with all the bonding pads. Okay. For C5, it's going to be metal 3 bonding pads. And that's a silicon wafer. For example, for our application, this is 2 by 2.5 millimeters dimension of the silicon die, the chip. So what's happening within the chip is actually it has many rows, many rows, like this. That's how the VLSI is being organized. Okay, a lot of rows. Every row has a top and bottom rail. Okay, like the one you laid out on Tuesday. Remember the inverter? You got two rails, right? VDD and ground. I have a PMOS here, NMOS here. Okay, so every row is one of the cells. So you're putting your like VDD, PMOS, NMOS, VDD, ground, PMOS, NMOS, okay, like this. So if, for example, this line is VDD, this must be ground, right? Okay. So you got a PMOS, NMOS, PMOS, NMOS, like that. So if you zoom in, it looks like this. You got your PMOS, NMOS, whatever. Okay. So to the layouts, VDD, GND. To save space, what we do is for the row next to it, we overlap the GND, so I'll put this one as a VDD. Okay, so the PMOS becomes here. That's a P. And you got an NMOS here. That makes sense? So you can save space for the overall footprint for the chip. So this is a zoom in area of this area. Okay. So we have the rows. They're plugging all the cells. It could be gates, could be different flops, could be any the mux, whatever cells, and they will be automatically plugged into these rows by the cadence tool. So eventually you can form like billions of transistors just by doing that. It's called placement, place and route. It's one of the steps for the VLSI design. Okay, it's called place and route. So place and route is going to insert all these cells into it and do the routing, some basic routing at the very beginning. Okay, so never see this from electrical VLSI. That's why we spend so much money and effort to get the cadence tools set up in the department. Okay. And you have to care about tape out. So the term tape out means you get a chip sent to the fab for fabrication. So you care about tape out. So when you do your VLSI design, you care about the real product. Okay, people have been saying, hey, if you just get the PDK, all the libraries and cells from TSMC, and then you do your design. You can mentor senior students, and you can even use the 28 nanometer technology. I mean, which is something we cannot afford, right? You can even use 20. You can even use 7, even 2, 5. Doesn't matter. You are not typing out anything. You just gotta send NDA and get the files from TSMC. You can start doing the designing, so get a lot of experience, which is okay. We can definitely do that. But the thing is, if you don't care about tape out and you ignore a lot of key points for fabrication, for example, the rolls, a lot of restrictions of the place and route. You just get some design, let the cadence tool run everything by itself. You got a design, you think I'm done, claim I'm done, right? But if you really the target is taping out, so you have to go through every single step towards the end, and then you'll meet with the people with from Mills, right? There will be a meeting before the deadline of the tape out. So you meet with 4 engineers from the company, and they will look at your design and get in the form signed, and then you can send it out. So it goes through the entire workflow. Will be really beneficial for our students and for the this class as well. But not the case of using open source tools. Only using Cadence and follow the entire workflow will get you that experience. Yeah. All right. So now let's come back here. By looking at this, this is going to be part of that role. Okay, this is the whole thing. And you take a part of it, right? Take a part of it, and you will start designing your gates into these two rails, power rail and ground rails, 2 rails. Now it makes sense, right? Why we are putting everything into that, within the 2 rails, right? So because that's one row in the chip. So start doing that. We have inverter, P, N, got this shorted, power. Okay, that's one inverter. Here's the poly. That's the first inverter here. And I have another inverter for B. Okay, that's another inverter. And you need two AND gates. 2 AND gates. So AND gates have 2 parallel PMOSes and 2 parallel NMOSes at the bottom. I'm going to show you how I'm going to draw that. So how do you make a parallel transistor? You do this. The way that works is, you see, because that's actually more complicated. So AND gate is a NAND gate with the inverter. That's the AND gate. It's a lot of work. And you need 2 of them, just one. You need 2 of them, and then you need an OR gate. OR gate is going to be a NOR gate with an inverter. Right? You can keep going, and then when you are done, you start making the connections, right? A and B ports, and these are the gates for these 2 transistors. So the reason I'm showing you this is just to let you know why this is not very convenient, and it's not the best way to do things. Okay, when you're trying to design the layout, because you have the schematic, assuming that you are manually designing everything, you know the logic. From the logic, you get into the schematic, the gate level logic, gate level schematic. From the gate level schematic, you draw the layout, right? You make the connections and chart DRC, check NCC or LVS, all matches. Done. You can tell people, hey, I just built a layout for the XOR gate. In the future, I can directly drag and drop this gate, XOR gate, into my design to form a larger scale of layout circuit. Okay, so that's the conventional way of doing that. But however, you can see this is not really convenient, and we have a better way of doing this. You have a lot of empty space here. Bad. Now let's see. XOR y equals a not b, or a b not. Let's add 2 bars on top. Split the bar and change the sign. Split the bar and change the sign again. The goal is to have a universal bar on the top. Covers everything. That's a goal because that's what the AI logic schematic tells us, right? So I told you guys on Monday, right? So we don't have to keep asking ourselves why. We already proved everything on Monday. Let's just keep using that. So the goal is to convert everything and put everything underneath the bar. It's one universal bar on the top, cover all the logic. And we can do this a little bit further. These are zeros. Something or zero is still that thing. So it's not changing anything. So what is that logic? So this guy is actually XOR. So that's why you know that XOR is basically XNOR inverse. Okay, that's a conclusion. All of you should know. You probably learned this already in logic. We forgot about this. So XOR is XNOR bar. Okay. It's not important here though, but we just need to know this logic so we can design our schematic. So here's the logic. Here's the desired logic. So we're doing an XOR gate. So XOR gate is XNOR bar. Okay. A B and A not B not bar. So start with unlogic. Unlogic is spiking parallel PMOS transistors. OR logic, you're expecting these two entities are in series. Always think about the NAND gates and NOR gates structure. Okay, so down here, this is unlogic. So unlogic, think about the NAND gates. It's chicken legs. So it's one line in series, A and B. Here it's going to be A not, B not. And that's it. So that's the schematic. I'm going to show you how to design a layout out of this, okay? How to design a layout out of this. We use a method, it's called stick diagrams. Because you already felt the pain of drawing all the squares, right? So let's just use the PMOS. So that's a two diffusion, that's a channel, and that's a gate. 2P plus and one gate. Two N plus one gate in the middle of the channel. Okay? So in electric VLSI, remember what this looks like? This, right? So it resembles it pretty well. We just don't have to draw the squares and boxes and VS. We just represent all these ones, simplify everything using these marks. Make sense? So you can draw the layout a lot faster. And one thing I want to introduce is if you have parallel transistors, how to deal with that. That's two transistors. How many transistors you look at the gates? How many gates? How many transistors? So two gates. And I always want to put them in one-liner design. Okay, one-liner design because it saves space. And we can always figure out parallel connections, series connections, even though they are in a one-liner. I'm going to show you how. Okay, so that's VDD. And these are the two PMOSes. I'm telling you, I can make them in parallel. Okay, there are two different ways. So this will be in parallel, and these lines are metal 1. Are they in parallel?
Yeah.
It's one signal line current stream coming down from VDD and being split. Goes through the channels, two channels, and then coming to this point, common point. So that's in parallel. I can do it in a different way. Same thing. This guy, you rotate it. Okay, see, one line, two lines coming into this line and merges to this line. Okay, that's in parallel. So it's the same shape as this guy. So two lines merge into the middle and come out from the middle in parallel. So these are equivalent. Depending on the structure of the circuit, you want to use, sometimes use this one, sometimes use this one, just to make your life easier, right? So it's based on which one's easier. You have to consider a lot of things, right? So if you do this, you are probably not expecting any signal from the middle because this is metal 1 and there's no room in here to route the metal 1. I have to drill a via and go to metal 2 and then cross the metal 1, drill a via again, go down to metal 1 and do the routing. So if you're doing this, you're not expecting any metal 1 in the middle, right? Because this is right in metal 1. This is metal 1. Make sense? You just have to consider the overall design. That is why we need stick diagrams to pre-plan, to just have a plan for the what kind of layers you want to use for the connections. It will never be perfect, but there are better options than less better options. So we don't have a lot of large-scale assignments to let you guys hand draw the stick diagrams to design a layout and implement it to VLSI, electrical VLSI. But you guys should know that a better way to do that is you purchase a lot of pencils with different colors, the pencils, colorful pencils with for kids, for Walmart, and then, so you different layers use different colors, right? Metal 1 use a similar color like a light blue color, poly is a pink, and so in that way you can pre-design your layout on paper. If you see there's a cross short circuit, you just avoid, you eraser to get rid of it and then find a new route. Okay, so by doing that, you take some time on the paper first, and then you go to a layout. You can directly implement it. Just copy it to a layout. Make sense? Okay. That's two parallel transistors. So you have another two parallel transistors in series with it. How do we deal with that? So these are two. So how to handle these PMOSes? 4 transistors, right? 4 transistors. So we need the 5 nodes. Here VDD, 1, 2, 3, 4, 5. That's a channel. 1, 2, 3, 4. 4 fingers or 4 gates means 4 transistors. I'm assuming that I can do it in the one line, in the one-liner. If I fail, I will just break it in the middle and find a better way. But by far, I think all the examples and is asking you guys to do a one-liner design. So it's going to be one-liner. So I directly just put everything on just in one line. That's why you are seeing this, right? Even though they are in parallel, in series, but I believe I can use the one-liner to get it done. And now let's see if that's the case. Okay? I'm going to show you the solution first. Probably no, let's do the incorrect one first. So two parallel ones. I'm trying to pick up, which option. You have two options, okay? So I'm picking up. Which one? This one, okay? Let's pick up this one. All right? Then what's next?
You'd have to do the same on the other side.
Huh?
You have to do the same on the other side, right? So
You do the same on the other side, like this. What is this? So these transistors don't have a direct connection to VDD. So if you have a connection here direct to VDD, that is incorrect. So this is wrong. Because these two transistors are below these two. And these two, they do have their sources shorted to VDD. But these are getting current from the drain of these two PMOSes. Keep that in mind. There's no direct connection to VDD. So if I do this, okay, for these two, okay, boom, merge, got a current out. Merge, get a current out. So look at this connection. This connection need to be connected to the other two sources of the PMOS transistors. However, this guy in the middle, this middle guy belongs to these two PMOSes. There's no way that I can get this out to these two PMOSes. You know what I'm saying?
yeah.
So that's not a, use this one for this example is not working. It's not going to work. So to pick up this option, okay? And why is this going to work? See? One current stream from the VDD power source and split and merge. Okay? So now I get this one. It's just next to these two transistors and makes things possible. So I can treat this node. Keep in mind, this node is going to be this node. All right? So this joint here is going to be this joint. And then the only thing I need to do is just to split this joint into two current streams and to go through these two transistors. How? From here, split into two. Where are these two transistors? Where are these?
On the right.
Here, right? That's the two channels.
Yeah.
How can I make this node become a major node and that current stream can go through these two channels evenly?
Connect to the one that's on the left. Like
If I do this, would that work?
no.
Would it?
Hmm?
Yeah, because you draw it back and then it goes to both of them and then goes back out, right?
Mhm.
Yeah. That'll work.
It's gonna work. So these two nodes are shorted by the wire, so they are considered as the same node. So these two nodes being shorted by the wire, so it's gonna be this node. Okay? And that node got two current streams, and it's gonna merge into the middle and then coming out. That's gonna work. So that's the solution to these 4 transistors over here. And if you run this, if you do a layout like this, and you do a schematic like this in electrical VLSI, it's gonna pass NCC. Even though it looks so different, right? It's gonna pass NCC. Okay? One question. How do you want to label the gates? You got A, B, A not, B not. How would you like to label them? Does it matter here?
Yes, you could,
These two, A, B first? Doesn't matter, they are symmetrical, right?
yeah.
Let's say A, B. What about here?
But also,
No order, doesn't matter. A not, B not. We can do it for now, but we probably have to change it when we have the NMOS layout as well. But now A, B, A not B now is fine. Okay? Now let's go to the NMOSes, which is a lot easier. Look at the NMOSes here. We use circles to represent N plus, right? So NMOSes, you have a ground, 4 transistors, 5 nodes. Assuming that the output from the PMOS is like a line here, right? So it's basically being split into 2 branches, and each branch has 2 series transistors. That's pretty easy because I can directly just do this. Okay, it's gonna split and go to ground. Any questions by far? That's N plus, right? Here. That's N plus.
I guess because they're in series, you don't have to do additional connections, right?
These are connections.
Like, because you have the 2 branches of series NMOS.
Uh-huh.
Yeah, so that's like it's splitting into each branch. And
Yes.
going.
Yes, exactly. Yeah. So by combining them, just to remember, how do we do the PMOS? This. Right? And then this. So that's a major part of the stick diagram for this circuit. Okay? And now let's talk about the gates. How would you like to organize the gates? See here, for the series transistors, the order matters. Why? Because the B transistor is directly shorted ground, and the A transistor is directly shorted, is in the middle of the B and whatever the PMOS is, right? It's in the middle. So the order here matters. So if you're looking at this one, for example, this branch to the left is the left branch over here, right? So which one should be A, which one should be B? I mean the gate.
I guess the left side should be AB.
Which is A, which is B here?
A first. Well, B on the left, A on the right.
Yes. Because that's G and D, right?
Yeah.
That's VDD. Now the order matters. What about this guy?
A on the left, or A not on the left, B not on the right.
All right. Now, previously we are saying for the PMOS we can label it as A, B, A not, B not. Okay, so here's the same circuit. Do you want to label them A as A, B, A not, B not again? Or anymore? Why and why not?
It doesn't matter because now. I mean, we still have to do AB on the left and B A not B not because AB on the left was the top part and the bottom part is A not B not on the right.
Yeah, for the PMOS it doesn't matter, right?
Yeah.
But which is better option? Hmm? Yeah? Why is that? Why is that helpful?
So you have shorter routes.
Yes. So B, let's just use the B here because they are same B's, which means the same signal lines, same node. Let's just align them, right? So BA, A not, B not. Let's align it that way because you have to do this. That's a poly. Drawing a straight line is way better than crossing them because crossing them is going to cause short circuit. So all the gates are polys. If you want to cross it, you have to drill a hole to metal one and drill it back down to poly to make the connections, which is bad. So when you are designing a layout, you should align them, right?
And that center wire is the output, right?
That's the output.
Yeah.
That's metal one. So it's not shorting. This is poly.
Yeah.
What is the output? Where is the output? Which layer?
M1.
Yeah, where is the output? Here, right?
Yeah.
What is the logic? XOR?
It's
It's XOR, right?
yeah. It's yeah, y equals.
What are the inputs? Yeah, all these are inputs, right? I mean, you can imagine you'll need inverters to invert the signal of the A and B's, but there will be. So very quick question here. So for the poly lines, usually the signal comes from the left, for example. How could you introduce signals into the poly lines? These are inputs. Polys are inputs, right? So how to get the inputs to it? Which metal layer? Which?
The N2, right?
Remember that poly? You introduce a little poly, right? And then immediately drill a hole here.
Oh yes.
Okay, that's poly to metal 1. What about this one? You shift it down a little bit and drill a hole to metal 1. Same. Okay, then what? You just got a metal 1, right? Got metal 1. So that's the inputs of the gate, and that's the output. So that's at our beginning we were trying to lay it out this way using the gates, but that's the same logic. We can implement it just by doing this. It's getting optimized a lot. It's gonna save probably 3 times less of the footprint as this one is taking, right?
Yeah, because basically, it seems like the stick diagram is allowing you to like overlap, kind of what we were doing in lab the other day, and having the actual transistors overlap with one another.
Mm-hmm. Yeah.
Okay, so then you can like compress them down. Okay.
Yes. Yes. Otherwise, there are still individual gates, right? You are placing individual gates in here and make the connections by looking at the gates level circuit, and now we directly handle the transistor level circuit. So with a smaller circuit, it's not just a less footprint, but also it's improving the speed as well. It's going to take in a lot faster signals. These ones will have a lot of propagation delay in the middle of the gates, and there will be like hazards as well. But this doesn't exist. Okay. Let's look at another example really quick. For one more example. For 3 parallel transistors, how do you deal with that? 3 parallel transistors. This. Stick diagrams of this guy. So you need a 4. And even though this circuit it looks like complicated, but it only has 2 parallel transistors, right? Still easy. But what about 3 parallel transistors? You got 1, 2, 3 fingers, and here's a VDD. Can I make that happen? One liner. The one liner looks like everything's in series, right?
Yeah.
So if you have like a million transistors in series, you don't have to worry about that. One liner can definitely solve the problem. Series, right? Done. But for whenever it's getting parallel and series combined, it's making things complicated.
Yeah.
So about three in parallel, I'm still trying to do everything in the one liner, but how do we deal with it?
You still have to do the skip one, so like go from.
Where to get started though? I mean, no. Here?
Yeah.
Where do you want to connect to the VD first? Because you have 3 terminals connect to VDDs. If I do this,
Or this one.
this.
Maybe.
So what's happening is, here's a VDD, here's a VDD, right? It's the same signal line. You can think about that. It's just one node, and current goes down here, and being split into 1, 2, and 3. So 1 is going through this channel. This is 1 transistor,
Yeah.
and 1 and 3. So it's 3 in parallel, for sure.
Yeah.
And then all the 3 signal, all the 3 currents are merging into 1 node. See? Because I'm using this wire to connect these 2 nodes. So eventually this is just 1 node. So they merges into 1 metal.
Okay.
So it means this piece of metal here. And that's the standard way of doing 3 parallel transistors. And you guys have to memorize it. You just don't have to think about this every time. So 3 parallel transistors is basically just this. Okay? That's how I make the connections. That's it. This.
Yeah.
Every time, just do this. If you see a 3 in parallel, just do this. Okay? What about 4? Let me show you how to do that, okay?
Say you do the 4 down from
That's a hint, okay? I'll let you guys draw it. Alright, think about this after class. You have a lot of time, and let me know on Friday. I'll take the time to the quiz. Make sure you guys have the time to